Lagrangian mechanics. That's what we're going to talk about. You don't need to know anything about Lagrangian mechanics because I'm going to give you a complete introduction. Just a note, I have done this before. I made a video. I made it as a presentation, and it took a long time to make. And I went back and looked at it, and I'm not super happy with it. So I'm just going to try again doing it on paper. I feel more organic on paper. Also, just a note, I'm using a new camera. I'm using my iPhone now just to see what happens. Okay, let's look at two problems. The first is this. This is a mass connected to a spring, and there's a drag force. So as I pull this mass, there's a spring force if I displace it from the equilibrium, but as it moves, there's also an air resistance force. So in the x direction, I can write Newton's second law as the net force is mass times the acceleration. So just a quick note, x double dot is the second derivative of x with respect to time. That's how we're going to write that. And so there's my spring force, negative kx, and my drag force, negative bx dot. I mean, this is a complicated problem, right? Because you have an acceleration, a constant position, and a velocity term, and so it's like, I don't know what I'm going to do. But it is indeed solvable. In fact, I have a video on this. I'm not going to do it right now, but I can solve this equation by dividing by the mass and getting a differential equation, and I get the following. X as a function of time is going to be e to the negative beta t, x0 cosine omega 1t plus v0 over omega sine omega 1t. So omega 1 and omega and beta, they're all just constants relating to the thing. But the point is, I did it, right? You can do it. You can use Newton's second law to solve this problem, even in a complicated situation like that. Now, the next problem I want to look at is this. This is the mass thing swinging on a string, a pendulum, a simple pendulum at that. And this is often covered in introductory physics courses. But it's actually a super hard problem, right? Because let's suppose I want to use Newton's second law. So I'm going to write the vector form F net is equal to, I'll just write it as ma, and that's going to be t plus mg. Okay, so, could I get a differential equation from that? Well, it turns out kind of no, right? Because I know the value of the gravitational force, but this thing up here is mean. The tension is very mean. Because what is the value of that tension? I can't just plug in an equation for the tension. In fact, the tension is what we call an equation of constraint. So the value of this tension force is whatever it needs to be in order to make the ball move and not get further away from the pivot point than the radius. I'll call that r because I don't want to use L later. So it does whatever it needs to do. I'm gonna be you, right? I'm gonna be you and do whatever I want. I'm going to be there for you. There's no equation. See, I have an equation for the spring force. I have an equation for the air drag. So that's good. Okay. So how do we solve that problem? I'm going to show you one way to set it up. So one way to solve this problem is say, well, look, the motion stays in this circular path. So what if I use polar coordinates? So in polar coordinates, video down below, I can write the following. I can say F net is going to be the mass times the acceleration in the r direction, which is going to be this way, r hat, and then theta hat is this way, theta hat. So it's going to be the mass times the acceleration in the r direction, but you have to convert to polar coordinates. It is not an easy thing because these unit vectors change directions as you move around. So the unit vectors are not constant. So you get the following. R double dot minus r theta dot squared r hat plus m times the acceleration in the theta hat direction to r dot theta dot plus r theta double dot theta hat. Sorry, cut that off right there. And the nice thing here is that if this moves in a circle, then r is some constant r dot equals 0, r double dot equals 0. So I actually can do this problem. I get the following. I only have a force in the theta direction that matters, so the tension just falls out. I don't even need it. So if this is the angle theta, then the force in the theta hat direction, F theta, is going to be equal to, theta hat's that way, negative mg sine theta. And that's going to be equal to the mass times, now right here I have r dot, which is 0. So I get mass times r, which is big R, negative, and there's a negative, theta double dot. The mass cancels, and I get theta double dot equals negative g over r sine theta. And that's the solution, okay? It's not a full solution, but it's a differential equation, and that's good enough for now. The goal from Newton's second law is to get a differential equation, which I have right there. It's already done. This is not a differential equation because t changes. So the problem you can see is forces like this, forces of constraint. We don't know what they are. We can't plug them into Newton's second law, so it's difficult to work with. Okay, so let's look at another problem that's actually quite easy and that you could do, and I'm going to show you the Lagrangian way to solve it. So suppose I have ground and a ball, and I throw it up with some initial velocity, and it goes up, and then it comes back down. So now suppose that I want to plot the trajectory, the y motion of this with respect to time. So it starts at some time t1, and it's going to go to some time t2, and it starts at some y position. Let's say it's right there. This is y. And I want to know what it's going to do. Well, it could go, like this. It could go like this. We know the answer, right? It's a parabola. It could go like that. These are all different trajectories in the real world. Well, it turns out that if I calculate the following, this thing called the Lagrangian, I'll write it out Lagrangian because it's important. Lagrangian. It's very easy to misspell things when you're writing things live. I'm just letting you know. L equals T minus U, where T is 1/2 my dot squared. It's the kinetic energy. And U is the potential energy. In this case, I have gravitational potential energy, mgy. So if I have that Lagrangian, then it turns out that I can calculate the action. So the action is going to be an integral of from t1 to t2 of L dt. So if I calculate L along this path, the Lagrangian, kinetic energy minus potential, and then I integrate that over time, I get the action. So here's the cool part. It turns out that the actual world path, the real trajectory, is when S is stationary. Stationary. It's really hard to spell, I'll promise you that. So that means it's sort of like a max-min problem, but it could be, as long as the derivative is 0 with respect to the variables. And this is actually not a max-min problem. It's much more difficult because we want to find the path. We want to find the function for which L is minimized. And for which S is minimized, which is an integral. So you're trying to find a function. You're not trying to find a value. And you're trying to find the minimum value. And that's pretty complicated. However, it turns out that there is a way to solve a problem like this where you want to minimize the function, find the function that minimizes an integral. And that's called the Euler-Lagrange equation. Euler-Lagrange. Why am I writing out all these things? Do I just want to make mistakes? Lagrange, see? Lagrange. Okay. So it turns out if my variable is y, then S will be stationary if the partial of L, the function, with respect to y, minus the time derivative. Oh, gosh. That spelling thing threw me off. Let me rewrite this. The partial of L with respect to y minus the time derivative of the partial of L with respect to y dot is equal to 0. This is how we're going to find our world path, our trajectory, by making sure that it satisfies this equation. So let's do that for projectile motion, and then I'll do it for the pendulum. And then I'll talk about the future. Okay, so here we have, actually I can trace over that, look at that. There's my ball, V, and then I'm going to say T equals 1/2 m y dot squared. That's pretty straightforward. I'm going to say U is mgy. So L is going to be equal to 1/2 m y dot squared minus mgy. Now what I want to do is to use that expression for the Lagrange equation, the Lagrangian, and plug it into the Euler-Lagrange equation. So remember, it's this. Partial of L with respect to y minus the time derivative of the partial of L with respect to y dot is equal to 0. So let's do this first part right here. The partial of L with respect to y. Okay, so when I'm taking the partial derivative, I have a y term right here, but that's y dot. And so in fact, I can treat that as constant. So this whole term right here is just a constant. So the partial with respect to y of that is 0. And then the only thing here is a y, so the partial of negative mgy with respect to y is just going to be negative mg. That wasn't too hard. Now I have two parts here, so I'm actually going to take the partial of L with respect to y dot. The partial of L with respect to y dot. So here, this term has no y dot in it, so it's essentially constant. So I don't have any derivative of this. I mean, the partial with respect to y dot 0. Over here, I have a power rule. Right, I have only a y dot, so I bring the 2 down. I have 2 over 2. I'll write it out, 2 over 2 m y dot, because it's 2 minus 1, and that's just equal to m y dot. Now I need to take the derivative of that with respect to time. So I'm going to say the derivative with respect to time of the partial of L with respect to y dot is going to be the derivative with respect to time of m y dot. And that's actually pretty easy because there's no time dependence. This is an actual derivative, right? Not a partial. And there's no time dependency on the mass. And so I just have mass times the time derivative of y dot, which is m y double dot. So if I put that all together, I get negative mg minus m y double dot equals 0. And if I add that to the other side, I get m y double dot equals negative mg, or y double dot is negative g. That's actually the solution because that's a differential equation. It's a very easy differential equation, but this says the acceleration is constant. And we already knew that, right? But it's just showing you an example of how this would work in Lagrangian. Okay, now let's do the pendulum because it's a little bit more complicated, but we don't have to use polar coordinates. So let's go back to the pendulum. So here I have a mass. This is length r. It's constant. That's the angle theta. And this is m. So the key thing here, the first thing is to find out, I don't have to use x and y. I can use any coordinates I want. We call these, I'm writing down things again, and I shouldn't, generalized, see? Gen coordinates. I don't know why. It's just your mind just goes boom sometimes when you get stuck in a spelling thing. I can use whatever coordinates I want. And in fact, we often write the Lagrangian as this. The partial of L with respect to qi minus the time derivative with respect to time partial of L with respect to qi dot equals 0. So qi and qi dot are just any generalized coordinates. They can be anything. Any coordinates that describe the system. So the first thing we need to do is to determine how many coordinates we need to define the system. Well, in this case, how many degrees of freedom are there? How many coordinates do I need to completely describe the system at whatever position it's at? And the answer is just 1, right? This one angle completely describes the system. So I can use theta as my coordinate, okay? So that's going to be my generalized coordinate. I don't need to know about x and y. But I do need to find the kinetic energy. I do need to find the potential energy. And that's not completely trivial, but it's doable. And I know it's not fun to say this, but the trick is to go back to Cartesian coordinates. So in Cartesian coordinates, I know this. 1/2 m x dot squared plus y dot squared, and u is mgy. So if I can get a relationship between theta and x dot and y dot and x and y, I can find my potentials and everything will be great. Okay, so let's write this. Let's call this y. That's, yeah, and that's x. So I can say y is going to be equal to negative r cosine theta, right? Because if this is y equals 0 up here, I'm going to call that y equals 0. And you don't have to. You can pick it wherever you want. Then this side is going to be the adjacent, so it's cosine theta. And then x is going to be r sine theta. So I can go ahead and find my potential because it depends on y. So u is mgy, but y is just negative r cosine theta. So that's pretty easy. Now up here, what I'm going to do is take the derivative of x dot and y dot and then add them together. So let's start right here. Y dot, is the derivative of y dot is going to be the derivative of this. That's with respect to time. So I only have one variable that depends on time, and that's theta. So the derivative of cosine theta is negative sine theta. So I'm going to get r sine theta. But then I have to use the chain rule and take the derivative of the stuff on the inside. So the derivative of theta with respect to time is theta dot. Now you see I left a space there because I was thinking ahead. And then I can do the same thing over here. X dot is going to be the derivative of this with respect to time, which is r theta dot cosine theta. Now I need to square these two and add them together. So because that's what goes up here in the kinetic energy. So I'm going to write x dot squared plus y dot squared equals, okay, so this squared is going to be r squared theta dot squared sine squared theta, and this is going to be plus r squared theta dot squared cosine squared theta. I can write this as r squared theta dot squared times sine squared theta plus cosine squared theta. And then sine squared plus cosine squared is, surprise, equal to 1. So it's just going to be r squared theta dot squared. So now I have my potential. I have my my derivatives. I can find the kinetic energy. It's 1/2 m times that. And so I can write my Lagrangian. So I have L equals 1/2 m r squared theta dot squared minus the potential, which was it was plus mg r cosine theta. I feel like there might be minus sign. Let's just double check. So there's a minus sign, and I had minus and minus. I think this is okay. I think that's okay. So I only have 1 degree of freedom, so I only have to do Lagrange equation, the Euler Lagrange equation once. So remember, I'm going to have the partial of L with respect to theta minus the time derivative of the partial of L with respect to theta dot equals 0. So let's do this part right here. The partial of L with respect to theta. This is going to be, there's no theta here, there's a theta dot. But there is a theta here. So the partial of this with respect to theta is going to be minus sine theta. And I don't have to have a theta dot because I'm taking the partial with respect to theta. So I get minus mg r sine theta. Now I'm going to take the partial of L with respect to theta dot. The partial of L with respect to theta dot is equal to, well, there's no theta dot term here, so I only have that one. So I use the product rule again. I get 2 times 1/2 is 1. So I get m r squared theta dot. Now I need to take the derivative. The derivative with respect to time of the partial of L with respect to theta dot is going to be equal. There's the only thing that depends on time is theta dot. So I get m r squared theta double dot. Now if I put this together, I get negative mg r sine theta minus m r squared theta double dot equals 0. Now I can add that to the other side. I get m r squared theta double dot equals negative mg r sine theta. I'm going to divide by mr squared, and I get theta double dot equals negative g over r sine theta. And that's the exact same differential equation I got before. And you may argue one way is better than the other, that polar coordinates is better, I'm team polar coordinates, and I respect your decision to say that. But let's look at another problem that I'm not going to solve, and then I'll set up two problems that I'm not going to solve. Suppose I have this. Oh, we just did that problem. No, wait, we didn't. This is the double pendulum. So now I have two angles, theta 1 and theta 2. So this, if you use Newtonian mechanics, you're in trouble, right? Because if I look at the forces on, this is called this mass 1 and this mass 2. So mass 1 is going to have a gravitational force, m1g. It's going to have a downward pulling force, t2. It's going to have an upward pulling force, T1. It has two tensions, and I don't know either of those. They're both forces of constraint. For mass 2, I have the downward force. You think, oh, that one's easy, m2g, and then I have a tension, so it's just a pendulum. It's not a pendulum because this does not move in a circle of radius r. Let's call that r. Let's call it the same r. Because that's theta with respect to that point right there, but that point's moving. It's not doable in Newtonian mechanics. Not really. Okay. However, it is possible to write kinetic energies in terms of x and y's. I can write the kinetic energy of mass 1 is the same as what I just had. The kinetic energy of mass 2, I can find that in terms of the x1 values and the y1 values plus this theta 2. And I can take the derivatives. It's a little messy, but you can do it. And I have a video on that. And I'll probably forget to link it down below, but I do have a video solving the double pendulum. Let's look at one other problem that's a little bit more doable and fun, and I'll solve it later, even though I think I already did. So suppose that I have this pendulum. So I have m, r, theta. But here I drive the pivot point. So this has an x value, let's call it xp, as a function of t is a cosine omega t. So this thing oscillates back and forth like that. I can't use polar coordinates now because it's not moving in a circle. It's got this jiggle part for it, and I call this the jiggle pendulum. Maybe some other people do too, but that's my jiggle pendulum. So in this case, it is possible, it's still just 1 degree of freedom. And it is possible to get the kinetic and potential energies. It will have this other term in there. And so when I take derivatives, it makes it a little bit more complicated, but it's doable. Okay, it is indeed doable. So those are some examples. So in the end, when to use Lagrangian equation? When Lagrangian. So number one, you want energy conserved because you're dealing with an energy equation. Well, mostly conserved. I mean, that doesn't say energy is conserved. It doesn't have to be. How about this? No non-conservative forces. Like friction. Friction is the greatest one. Now, there is a way to get that to work, but it's very complicated. But in general, if I had a frictional force in here on this thing, it's really difficult to incorporate that into the Lagrangian, and so it doesn't really model the system very well. But I want to use Lagrangian when I have forces of constraint. That's the key thing. So if an object is forced to move on a particular surface or with a string or something like that, Lagrangian really makes sense. It doesn't solve the problem. It gets us the differential equation, and that's the key. Once I get the differential equation, I could do some other method to solve the problem, but I can't get a differential equation straightforward with Newtonian mechanics. And that's the big difference. So if you know what all those forces are, Newtonian mechanics is going to work great. You get a differential equation right away. If you don't, then you probably should use Lagrangian. So I'm going to solve some more Lagrangian problems, but that's my very basic introduction to Lagrangian mechanics. I hope you found that to be interesting. I'll talk to you later.